Is the universe a hologram? What if everything you see, everything you touch, the entire three-dimensional world around you is a projection? Not a projection in the mystical sense, but in a precise mathematical sense. A hologram. The information that makes up your reality, including you yourself, might actually be encoded on a distant two-dimensional surface, like data on a cosmic hard drive. This is not speculation from the fringe. It is a serious hypothesis emerging from the deepest physics of black holes and string theory. The holographic principle suggests that our three-dimensional universe is, in a fundamental sense, a two-dimensional information structure. Volume is illusion, depth is derived. What we call space might be an elaborate reconstruction from a flat boundary we will never see. Welcome back to The Conscious Observer. Today we explore the holographic universe and what it means for the nature of reality. The holographic principle was born from a crisis in physics, the black hole information paradox. When matter falls into a black hole, it seems to disappear from the universe. But quantum mechanics forbids information from being destroyed. Information must be conserved like energy. So where does the information go? Stephen Hawking discovered that black holes radiate, slowly evaporating over time. But this Hawking radiation appeared to carry no information about what fell in. The black hole would eventually vanish, and the information would be lost forever. This violated a fundamental principle. Physicists struggled for decades with this paradox. The resolution, proposed by Gerard 't Hooft and Leonard Susskind, was radical. The information is not lost because it was never inside the black hole. It is encoded on the event horizon, the black hole's two-dimensional surface. Here is the strange implication. The amount of information a region of space can contain is not proportional to its volume, as you might expect. It is proportional to its surface area. This is deeply counterintuitive. A room should be able to hold more data than the walls enclosing it, but physics says no. The maximum information in any volume is bounded by its boundary, not its interior. This is called the Bekenstein bound. Applied to black holes, it means all the information about everything that ever fell in is somehow smeared across the event horizon, encoded in Planck-scale pixels on a two-dimensional surface. The three-dimensional interior is, in some sense, redundant. Everything happening inside is fully described by the boundary. This insight generalized into the holographic principle. Any region of space can be completely described by information on its boundary. The holographic principle received its most precise formulation in 1997, when physicist Juan Maldacena discovered the AD-S-CFT correspondence. AD-S stands for anti-de Sitter space, a particular geometry used in theoretical physics. CFT stands for conformal field theory, a type of quantum theory without gravity. Maldacena showed that a gravitational theory in a five-dimensional AD-S space is mathematically equivalent to a non-gravitational quantum theory on its four-dimensional boundary. These are not similar theories. They are the same theory in different languages. Every question about gravity and black holes in the bulk can be translated into a question about particles and fields on the boundary, and vice versa. This is holography made mathematically precise. A world with gravity emerges from a world without gravity. Three dimensions emerge from two. Space itself might be a holographic projection. If holography is correct, space is not fundamental. It emerges from something deeper, quantum information. Recent theoretical work suggests that the geometry of spacetime is built from entanglement between quantum systems on the boundary. Regions of space are connected because the underlying quantum states are entangled. More entanglement means closer connection. Less entanglement means greater distance. If you could disentangle two regions, you would tear the fabric of space between them. This connects to what we discussed in our entanglement episode. Quantum correlations are not happening in space. Space is happening because of quantum correlations. Distance, proximity, the very notion of here and there might be derived from patterns of information and entanglement in a more fundamental description. We do not live in space. We live in a projection of something beyond space. To understand holographic reality, consider how ordinary holograms work. A regular photograph records the intensity of light from a scene. A hologram records both intensity and phase, the full wave information. When light shines through a hologram, it reconstructs the original light waves, creating a three-dimensional image from a flat surface. The key insight is that all the three-dimensional information is encoded in two dimensions. Every point on the holographic film contains information about the entire scene. Cut a hologram in half, and each half still shows the whole image, just with less resolution. Now imagine the universe works similarly. All the information about everything in our three-dimensional space is encoded on a distant two-dimensional surface. We are the image, not the film. The projection, not the source. What feels solid and voluminous is a reconstruction from something flat. Is there any evidence that our universe is holographic? The ADS-CCFT correspondence is mathematically proven, but it describes a universe with a different geometry than ours. Our universe appears to have positive curvature, not the negative curvature of anti-de Sitter space. Extending holography to our universe remains an active area of research. Some physicists have looked for holographic signatures in the cosmic microwave background, the afterglow of the Big Bang. If space has a fundamental granularity at the Planck scale, as holography suggests, this might leave subtle imprints in the pattern of primordial fluctuations. Results so far are inconclusive. Other researchers have proposed laboratory experiments to detect holographic noise, the fuzziness that would result if space is pixelated. The Hole Knitter experiment at Fermilab searched for such noise and found none at the levels predicted by some models. Holography remains theoretically compelling, but experimentally unconfirmed. What does holography mean for consciousness? If you are a pattern of information, and that information is actually encoded on a distant boundary, where are you really? Here, in the three-dimensional world you perceive, or there, on the two-dimensional surface you can never reach. Perhaps the question is meaningless. Perhaps here and there are both valid descriptions of the same underlying reality. Your consciousness might be a holographic projection, a three-dimensional experience generated from two-dimensional data. This resonates with the insights from our earlier episodes. Reality is not what it appears. Observation shapes existence. The seemingly solid world rests on foundations of information and relationship. Holography adds another layer. Not only is matter mostly empty space, but space itself might be a kind of illusion, a useful reconstruction but not the fundamental reality. The holographic principle points toward a profound shift in how we think about physics. Traditionally, physics describes stuff, particles, fields, forces. Space and time are the stage on which the action unfolds. But holography suggests that information is more fundamental than stuff or stage. The universe is not made of matter, it is made of information, structured and processed according to rules we are only beginning to understand. Matter and energy are how information looks from the inside. Space-time is how information organizes itself. The physicist John Wheeler proposed the slogan "it from bit." Every physical quantity derives its ultimate significance from information theoretic terms. The holographic principle vindicates this vision. At the deepest level, reality might be a computation, an information structure of staggering complexity that generates the appearance of the world we know. We began this episode with a question. Is the universe a hologram? The answer from theoretical physics is possibly, and the implications are profound. Space might not be fundamental. The three-dimensional world might be a projection from a two-dimensional boundary. Everything you experience might be encoded, in principle, on a distant surface at the edge of the cosmos. This is not a diminishment of reality. A hologram is not fake. It is a different way of understanding what is real. The information is genuine. The structure is genuine. The experience is genuine. Only our interpretation shifts. You are not less real for being a projection. You are a pattern of information, conscious of itself, asking what information is. In our next episode, we turn inward to the strangest territory of all, the self. What are you? Where does personal identity come from? And what happens to the observer when there is no self to observe? Until then, remember, you might be a hologram, but holograms can ask questions. Keep observing.